Today's topic is evaluating limits using graphs. So we've talked a little bit about limits, mostly when it comes to end behavior. We're now looking at limits as we approach, instead of the ends, the infinities, we're approaching an actual point, some actual value, some value of x. So let's talk a little bit about what does it mean to be a limit. So when we're talking about f of 2 is a point. It's an actual dot on the graph. So if I say, what is f of 2, you would then go find the graph. So if I were to generalize that, f of x is all the actual points. It's the actual places on the graph. A limit is different. So we would write the limit of, remember how we say this, the limit of f of x as x approaches, I'll just call it c for now. Now this is what the graph intends to do. This isn't what the graph actually does, it's what the graph intends to do. So when I think back to what we did in behavior, the end behavior of our graphs would be things like the graph is going off to negative infinity or going to positive infinity. It can never get there, it's intending to get to those places, but that's what I'm talking about when I say the limit. It's what the graph meant to do, even if it didn't really do it. So if I were to compare down these two things together, they are linked, that these are always y values. These are always y values. So we look at the x, like for instance here, this would say, this is telling me that x is 2. So I would go to 2, and then I would trace up to where the function is, where the curve is, and that would give me a coordinate pair or a point. Over here, why don't we make this 2? I guess that makes sense. As x approaches 2, that's pretty crummy too. Let's try again. As x approaches 2, the graph is trying to do something from both sides as we approach. So the limit is what the graph intends to do. Whether or not there's anything there is up to the graph. All right, so let's look down here. Let's look at this notation. So there's 3 different ways that we can write up what the limit looks like. So I'm going to do a little zoom in here. We've got these two first, the limit from the left and the limit. This is called the limit from the left. So let me circle that and highlight this. So what this means, as you approach 4 from the left, not going left, but coming from the left. And then if I were to look at this one, says, what's the limit? What's happening to my function? This is how this is read. What's happening to my function as x approaches -4? This little plus means from the positive side or from the right. From the right side. Dang it, I gotta keep looking up here. Okay, so then these two together are a group of limits that are called one-sided limits. These are both one-sided limits because they are approaching the value -4 on the x-axis from one side. This is only coming from the left. This is only coming from the right. Now moving over here, this is another notation. Notice we have the limit. We have our function again. So this is saying what's happening to my graph, what's happening to my y values as x approaches -4, but there's no symbol here. That means that it's coming from the left and the right at the same time. You're looking at both sides. This is what we call the overall limit, or just the limit. You would just say, most mathematicians would just call that the limit, but it means the overall limit. It's what's happening from both sides. And now we look at this last case. Here we go. This is what I was talking about at the beginning. This is giving me an x value. This is f of x, right? So that f of x became f of -4. That means -4 is my x value. And this is saying, what's the function value? This is a point. This is the function value. In other words, it's the point. It's the actual dot that's occurring at -4, at x equals -4. Okay, so now let's go back up to our graph and try to analyze these. So the first thing it says is find the limit as x approaches -4 from the left. So here's -4, -1, -2, -3, -4. So this is the x value of -4. And what I want to do now is I want to track in. I want to follow the curve as I approach. So I'm going to be moving along the x. X is getting closer to -4. As x is getting closer to -4 from the left, I want to track to see what the actual graph is doing from that side. Now, you usually don't want to go way far away. Just go a little bit. So here's -4. Just go a little bit to the side. As I track in here, as x goes to -4, what does my y go to? As x goes to -4, my y tries to approach the value of 5. That means that my left-sided limit is 5. All right, now let's check it from the other side. What's the limit as we approach -4 from the right? So now I'm coming in from this side. Now look, this is what I'm talking about. Don't go way down here and start approaching, because when you approach, you're going to get stuck, boom. Or even if you go down here and you start to approach and you follow the curve, as x gets closer to -4, I'm following this curve. Well, I get caught into this thing that we know is an asymptote. So we'd be going up to pot, we'd never get there. So just go a little bit over. So go a little bit away from -4 on the x, track up to the curve, and then approach. So as I approach the -4 from the right, what is my y value approaching? It's approaching 5 as well. Okay, so the overall limit is just the one-sided limits compared to each other. You have an overall limit if both one-sided limits are approaching the same place. So if you're going to the McDonald's in town and I'm going to the McDonald's, I'm sorry, up here. If I'm going to the McDonald's in town and you're going to the McDonald's in town, we're coming from different routes, but where did we end up? At the same place. That's what an overall limit is. F of -4, this is literally the dot. So you just go to x is -4, boom. I'm not approaching anything. I'm saying what's happening at -4. I track up 5. So what do we call this? This is called continuous. You might think this was kind of boring because they all were the same answer. Yeah, it is. This is the simplest case. I started with the easiest one. Your function is considered continuous at x equals -4 if the one-sided limits, or if the limit and the point are at the same place. Let's look at some that don't come out to be that. So what are we doing? We're approaching -5 from the left. So I'm going to go up here to -5. This is where I'm approaching. So as I come in from the left side, boom. Now look, where are we approaching? We're approaching the y value of 1. Is there a point there? No. No, there isn't. That's not what a limit is talking about. A limit is always saying, what is this thing supposed to do? So this is supposed to reach a height of 1. It didn't reach a height of 1, but it's supposed to reach a height of 1. Coming from the right side now, don't go way down here, just go a little bit to the right of -5. Track up to the curve, and then track into x equals -5. What height are we supposed to reach? We're supposed to reach a height of 1. We didn't, but we were supposed to. So the overall limit, remember the overall limit is a comparison of the one-sided limits. So if the one-sided limits are headed to the same place, then the overall limit is also headed to that place. What's the actual, I'll talk about that in a second. Let's talk here. So what's the actual point? Now we're looking at what's happening specifically at -5. So I track to -5. I go up or down from there. Is there any dot? Is there any point? No. All we do is we go whoosh right through that hole. There is no actual point here. So we would call this DNE, which stands for does not exist. What do we call this situation? We call this a hole. A hole occurs when your limit exists, so your graph is approaching the same y value, but it doesn't actually get to that y value. So going back to our McDonald's example, you can kind of think of this. All right, you're going to a McDonald's. I'm going to a McDonald's. We're going a different route, but we ended up at that McDonald's. Great. We're eating our Big Macs. Now we go down here. Actually, I'd probably go with a quarter pounder with cheese now that I think about it. Yeah. Maybe a McChicken. Okay, anyway. Definitely fries though, right? Best fries are McDonald's fries. So down here is a different scenario. I'm going to McDonald's. You're going to McDonald's. We're both approaching McDonald's. So we're saying get to McDonald's at 5 o'clock. So it's 5 o'clock. We're at McDonald's. But what's happening to the McDonald's? There is no McDonald's. Somebody blew up McDonald's. It's gone. So we're still at the same spot. We're still together, but we're not. There's no McDonald's there. We're at the spot, but there's just a big hole in the ground. So hopefully that makes some sense between what a continuous function looks like. The McDonald's exists. You and I are both at the same McDonald's. You and I are at the McDonald's location, but the McDonald's is gone. All right, so let's take a look. Next one, x approaches 2 from the left. So now I'm approaching 2. Let's go with orange. Okay, so x is 2. 1, 2. Oops, sorry. X is 2. I'm approaching, so go a little bit over. Follow the curve in. The limit is saying where's the graph supposed to go. This graph is supposed to reach a height of -2 from the left. Go a little bit to the right. Track to your curve. Follow it into where x, it's approaching -2. So are you and I headed to the same McDonald's? Yeah, we're both headed to the same McDonald's. So that means our overall limit exists. Here's the problem. Somebody took the McDonald's and, I don't know, somehow picked it up and moved it, or they changed the store location and they didn't tell us. We didn't know. So we both headed to the same spot where we thought McDonald's was, but McDonald's is up and moved closer to the mall, let's say. My actual point is at 1. So you and I headed to up there on 3rd Street. We headed to the McDonald's. The McDonald's was the same. We both went to the same place. You went there, I went there, so we went to the same place. But McDonald's has closed at this location and moved to a different location. So this is what I call it. I don't know what the actual name, I've never heard the actual name of this. I call it a holy jump. It's got a hole and it's got a jump. I'm going to talk more about a jump in the next example, but no other teachers would know what I'm talking about when I call it a holy jump, but that's what we're going to call it in this class. What have we not used? Let's go with a nice purple here. All right, so now we're approaching 4 from the left, 4 from the right, overall limit at 4, and the value at 4. So here we are at 4. One, 2, 3, 4. So I want to approach from the left first. So here's x equals 4. Go a little bit to the left. Go to your curve and track what height your graph is trying to reach. Where is it intending to go? It's intending to go to a height of 3. Does it actually get there? Yes, but I don't care about that. All I care about when I'm looking at limits is where does the graph intend to go. Now I'm going back to 4. I'm going a little bit to the right, and I'm tracking that in as well. As I follow that in, that's trying to reach a height of -3. It doesn't get there, but I don't care. A limit's all about what it intended to do. It's intended to reach a height of -3. So what's our overall limit? Well, our overall limit is DNE. Because this, from the left, at x equals 4, the graph was trying to reach 3. From the right, the graph was trying to reach -3. They're not at the same place. Going back to our McDonald's examples, I said, hey, let's go meet at McDonald's. Well, you smartly drive to the one in Fruitport. That makes sense. I choose to drive to the McDonald's in Spring Lake. Are we both at a McDonald's? Yeah, we're both at 4. But you are at the one in Fruitport. I'm at the one in Spring Lake. Looks like somebody blew it up there too. But we're at different places. We're not at the same place. And that's what a limit is. A limit is, are we intending to go to the same location? And you went to McDonald's, I went to McDonald's, but we went to different McDonald's. That's why our overall limit does not exist. Our point, f of 4 is asking you what's actually happening at x equals 4. So when I go to x equals 4 and I trace up or down from there, the actual point is at a height of 3. This is what we call a jump. A jump occurs when one side of the graph goes to a totally different spot than the other side. So a Holy jump is where the graph meets at a hole. So I think of it this way. It comes into a hole, it jumps out for 1 millisecond, and then jumps right back in. So it's kind of like holy jump. So it goes in here, holy jump, 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 boom, go. A jump is where we go to, and our graph goes to a totally different location and then comes out the other side or approaches a different value. Where over here, this was just a hole. You came to the same, I came to the same. There was no point there, though. All right, and then finally, we're talking about x approaches -1 from either side. X equals -1. Oh, yeah, this is our good friend. As here's x equals -1. Go a little bit to the left. Track it in. Where's my y values going? Well, they're not going. Where's the graph intending to go? Down, 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 down. So the limit from the left would be -infinity. The limit from the right, from now I'm a little bit to the right of -1. Track the graph in. It goes up to +infinity. Are they going to the same place? No, and actually, anytime one of your one-sided limits are infinity, this is automatically DNE. Even if they're both going towards +infinity, can you ever actually get to +infinity? No, nobody can actually achieve +infinity. So whenever your one-sided limits are infinities, then you're always going to have a DNE. This is asking me what is the actual point, what's the actual function value. So as I go to x equals -1 and I track up and down, all I get is this asymptote. So there is no actual point. This is a DNE. And what did we call that? We call that an asymptote. So there's a couple of things that I want to highlight here. I think it's kind of nice to go through and just draw what these things are actually on the graph. So let me get, what would be a good color? I'll go with this other orange, I guess. Okay, what do we call this thing? Yep, this is called a hole. What do we call this? This is called an asymptote. What do we call this? This is what we call a holy jump. That's a jump that's where we approach a hole. We jump out for 1 millisecond and we jump right back in, and that goes out the other side. Holy jump. And then this is just called a regular jump. This is just a jump. It comes in, it jumps, and it goes out the other side. Or they jump, they don't approach the same place. So this is just called a jump. So there's a hole, there's a jump, and then there's called a holy jump. And then the last thing I want to kind of highlight down here on the side, if you'll notice, when our graph is continuous, when our graph has a hole, or when our graph has a holy jump, our limit, overall limit, which is the one that we really care about, the overall limit always exists. When you look at a jump or an asymptote, the overall limit does not exist. So I want to add that down here as a little reminder. For these three, limit exists. For these two, the limit does not exist.